Templates is a kind of very neat idea developed in the 80s by Bjarne Sustrup, and it has been regarded as slow and painful for many years until someone figured out how to implement them efficiently by using extensive inlining of functions, etc. So nowadays, let's say that you want to use templates as much as you can. While like in the 90s, if someone would say use templates, they will say you're crazy. The code will be 100 times lower. Right? But now, really, templates really works very well. There are two kinds of templates. There are function templates and there are the class templates. First of all, to be very specific, a function template is not a function. You cannot call it. To be able to call it, you need to instantiate it. Okay? A template is just a piece of text there. The compiler goes through that text and checks if there are some syntax errors, but it doesn't do anything more than that. It just checks if you're using symbols that really do not exist in scope or simple errors. If you have more subtle errors, they will not be catched there. It will catch when the function is actually instantiated. The mental model here is substitute the text. If I'm saying I want to call foo, with an integer template argument and pass 65, and that moment the compiler generates a function which is foo with an integer argument, and then it will write the code that calls that function. Only when you instantiate it, right? If I do foo char of 65, it will instantiate another function which has the instantiation for the char, etc. Plus, for functions, we can deduce the template argument. So we can write foo 3.14, whatever, and this is a double, so this will instantiate the function foo for doubles. And similarly for string, right? We'll instantiate another foo for strings. Something that might be interesting is this compiler explorer. Let's see if we can copy directly from where is it? So this compiler explorer is something that Paolo found out for me. I didn't know this. It's a very cool website. It has a very weird name. Like if you search compiler explorer on Google, you get it. It allows you to write code and see the generated assembler, and to break microphones. Okay. This is the code we cut and pasted from the slide, apart from the inclusion. And here you can see what happens with colors. You have a foo int. Now everything is actually in line. No, it's not in line. There's actually a function call, you see? Okay. Yeah, it's -0. Okay, good. So when I write foo int to 65, it will take 65, put it in some register. Can everybody see that? Should I zoom in? I'll zoom in. Maybe not. Okay. So if we go here, we go by colors. So this is where we call foo int 65, and you say put 65 on this register, then call foo int with the int signature, then put 65 in the same register and put the char, call the char function. For doubles, way more complicated. You need to put more effort to generate that value and then call the foo double. And for the string, it's even more complex, as you can see. You have to create the allocator, create the strings, pass the string reference to someone, and then you pass it. And then you go down here, and you should see the implementations. Foo int, foo char, foo double, foo basic string. Okay, and then static initialization. So what happens here? You instantiate only the function you called, right? That the guy didn't instantiate foo for every possible type because he doesn't know what the possible types are. Instantiate only the one that you requested. If you do -03, I guess you get some optimizations out of it. But since there is std out, it's probably, I don't know if it's worth showing. But this is the actual mechanism. Now, the name that you can see here, void foo double double, is very readable. This is actually the function that is instantiated. Apart from the fact that this is not really the name you will find if you go and look at your binary code. The binary code will be extremely more confusing. You will have the string foo sometime, and maybe the string double too, probably not. And we'll have all these strange characters and underscores and whatever. Because this is what C++ does, which is the name mangling. So it generates names that do not contain spaces, basically, or parentheses, because if you expose those names, the linker got in kind of trouble. So instead, this is like a pretty visualization of what the name will be. I don't know if you can actually see the mangled names here. Yeah, but okay, it's okay. Should be fairly clear, right? So in the mental model is that you substitute the text and you generate the function with that text in there. And you replace t, every time you find t inside the function, you replace with the whatever type is in there, and the type can be deduced instead of being explicitly specified. So what are templates? What do templates have to do with overload resolutions? Well, let's take the same code as before, but now we put like a foo implementation that takes a string by const ref instead of x, right? Before, you could see this one, we're taking x by value. When we do the string, when we do the text substitution, this will become a string here, and is passed by value. It means that this in principle, generates a string called the copy constructor. Actually, it should be visible in the code generated here. It should be visible. The copy constructor of the string, the pink one, right? Allocator, the basic string. So we construct this should be, the allocator, the structures, and one resume. Well, I guess. Oh, maybe it's too complicated. No, the structure. When do we call the thing? Call foo. Okay, call foo. you know. Yeah, it's too difficult to find out. Anyway, the copy constructor is basically code. If you don't optimize the code, usually this is create the strings on the stack, copy construct the version of X. So it's copying every character to the other guy. And this may be expensive. Instead, we can do, okay, well, if it is a string or maybe some other heavy type, I can specialize and you say void foo, in which I say string and then const ref to that string. So the string is not copied. It's just to take just a reference to it as a const reference. So it will work also with temporary objects and everything will work fine. And here, overload resolution kicks in, as the thing that we saw earlier. When the guy goes here and say foo int 65, so this is 65, you search for this thing. This guy does not accept an integer, so this is the only one that's left. When it goes for a string, it takes this one, which requires a template substitution, and it goes here that actually accept a string, so I don't need to do any specialization. So this one is more specialized than the template, and so will be picked up. Is it clear? Order matters. Well, if I have a function that takes 2 arguments. By the way, anyone surprised by this? By foo having t and u without variable names? In C++, you can simply put the signature there with the types. You don't need to specify the type of the name of the variable. This is just a signature. The name of the variables are needed only if you need to use the variable inside the function. Otherwise, it doesn't matter. Certain compilers actually complains if you specify the name there that you don't use inside your function body. So it's better to do this, so to not put the names if you don't use them. So now we have some foo, and we pass a standard string, and we pass a double, and we pass hello, and we pass 4.5. What happens here? Here what happens is that this hello, which is, what type is that? What is this hello? It's a const char. It's an array of const characters. It will be translated into a string, because t will be a string. So there is a constructor of a string that takes a const char. So it will be copy initialized or converted to a string. 4.5 is a double and will be passed as a double to u. So t will be string, u will be double. Everything is fine. If I do like this, as to the string and a hello and 4.5, well, that is still valid. The first argument is hello. As to the string is t, and is hello, is converted to a string. And 4.5 is deduced to be a double. So u will be double. Foo double hello 4.5, this is a compiler error, because the first argument is t, and t is double, and it tries to convert hello to a double, a const char pointer to a double, and this is the error message you will get. And the error you get is this one. Cannot convert hello, which is a const char 6, to type double. This is the error that the GNU compiler gives you. One important thing about templates is that the templates that is not a function, right? It's just a piece of text there that is waiting to be substituted, for the tokens to be substituted with something else. So the template must be all known before the instantiation can happen. Let's see if we have a template, a convert function that returns a type of, this is to, and takes a from as an argument. This one will have a syntax like convert a double d to integer. The first argument is 2, the second is deduced to be double, or convert char to, or int pointer, it takes a float to convert. This last one, it takes convert, which is a template, and the type deduction happens here because the type of this pointer is a function pointer to a function that takes a float and return an integer. So the return type is int, which is 2, and the input argument is a float, which is from, and this is actually instantiated. So this will instantiate, convert integer float. Even though it's never called in this code, right? It's just instantiated. You can force you can kind of force instantiation. And so there, the first argument is 2, the second is from. What if invert the to and the from? Now, because it makes more sense to say convert from to instead of to from. And you return to and you get from. Well, you must be explicit all the time now, because now you take a double as a first argument is the from type, which is d, and returns an integer. And you cannot do shortcuts. Basically, if you try to do shortcuts, you get into the problem before that the argument order matter, and you cannot deduce the right one. So surprisingly enough, the last one is actually the same line. So let's say that the first argument is double, the second is integer. So as before, the first argument is integer, the second is double. So if you want to get the right order, but these two lines are exactly the same because the argument deduction will work. The return type is integer, which is 2, and the float is the argument, which is the from. You can force instantiation. Any question? Beautiful? Doubts? The important things to remember is that the function template will be instantiated only when you give all the information. It will instantiate only the one you need and nothing else. But you need to be aware of the order of the arguments, especially if you are deducing some of the arguments. So class templates as function templates is not a class. It's a template. The template need to be instantiated, and you need to pass all the possible information for doing so. Problem is that there's no deduction happening here. You have to be explicit. So type name t has to be deduced. There's no way I can deduce that this is integer from this syntax. In principle, if these had the constructor that takes an integer and is the same type of the template argument, no way. The constructors you cannot deduce the template argument of a class. You need to specify it all the time. So when it is instantiated, then the object exists. What is the type of the object? X. The type of the object X is class underscore name angle bracket int. That is the type. Okay? Class underscore name is simply the template. Class underscore name int, that is the type of X. Which means that if I have a class name double Y, I cannot convert one into the other. They're not the same type. They're two different types. One important feature that class templates has, so function templates has overloads. So I can create specializations with overloads. With classes, I have something which is called partial specialization. Partial specialization is basically using string matching to try to find the best candidate for for the instantiation. So suppose we have our struct X, which has two template arguments, T and U, and we say, well, struct X can be specialized for the case in which the second argument is an integer, or for the case in which the first argument is a float. So what happens here? When I instantiate X char and double, what is the version that is instantiated? Is it number 1? Number 2? Or number 3? Number 1? Number 3? No, number 1. Right? That's easy because no one of the other one matches. If I do char and int, number 1, number 2, number 3, okay, number 2. And here, float and double, same, we'll instantiate number 3 because of the float. What if? What happens here? Number 1, number 2, or number 3. This is a compiler error. And the error is don't know which specialization to pick. Because I have a specialization with the float here, but I have one with the integer, so the number of template substitution I have to do is the same. No one is better than the other. I hang up. I give you an error. So in this case, to analyze what happens here, we need the template specialization partial order. So we have a primary template. So the template in which you have like all the template arguments and the struct doesn't have any angle brackets in there. So it's like this, simple and plain. That is called the primary template. And the primary template must be always available somewhere. All right? You cannot just have specializations. You must have a primary template somewhere. Then you have the case in which you specialize the first argument and the case in which you specialize the second argument, and they are basically at the same level. It doesn't know which one to pick. So to solve the problem, you need to put a full specialization here, and then you solve your problem, in which you put a full specialization. It's called full specialization, so no template arguments here, and then the float and int. In this case, this is the most specialized case that you can solve this ambiguity problem. Again, specializations are quite important. It's an important mechanism for many of the things that you can do in C++. And now suppose that we have our struct X, and our struct X is specialized for the case in which the second argument is actually a type X again, which with 2 arguments, and then T is repeated here. For some reason, not really a smart choice, but you have a type T that is repeated on these 2 cases. Actually, you should be writing this guy. This is why I didn't want to give your slides earlier, because there might be problems in my slides. So. Okay, let's hope that this works. Okay. So now we have a type name W. So our primary template takes 2 arguments, type name T, type name U. Now that the struct the specialization takes a type name W, whatever it is, and then X with 2 other arguments. And when we have yeah, this works. Okay, now, what happens when I instantiate X double and double? I go to the primary template because the second argument is not of type X. In this case, X with int, X int float, this goes to the specialization because the second argument is an X of something, and T will be int, U will be float, and W will be int. And now I can do X of int, of X of char, of X of int and void. I can use void as a template argument, by the way. Now, this is quite interesting because this is the mechanism in which Boost MPL library implements MPL vector. It's just a sequence of types. You can use it as a vector of types in your meta code. So it's never instantiated, but you can write here, this is kind of a list of types, which is an integer, a char, and an integer again. And the void is the end of the list, for instance. This is the basic for implementing these kind of tricks. If I call foo of A, and A is a double and double, this is another case in which a string matching kicks in. A is a type of double double. Foo takes a single template argument T, but it expects a types X of T and T, in which the 2 arguments are the same. Is it clear how that works? It's basically doing kind of string matching. It takes the type of A, which is X double double. Okay, this is X, fine. And T is double and it has to be double. If I try to call foo of C, in which the first argument in int and the other is X, it will give you an error that says, well, I cannot really deduce the second argument here. It's not the same as the first one. Type T is wrong here. I cannot cast to it. Again, when you do a recursive structure like this, X int float, in this second case, for instance, this is a specialization, right? Because the second type is X and goes here. And this guy does not have X as second argument. It will go to the primary template. So it will be a primary template for this guy and a specialization for the big guys. And this is how you can stop recursion when you do your type. Any questions? We have to see these things in action somehow to get used to it. But it requires some experience at the end. So hopefully with the template metaprogramming and generic programming, this thing will come much more useful. What I was trying to do here, replicate the slide. Okay, this is an exercise for you. And this is the evaluation order of the arguments. You can use default template arguments. So you can say the template, they have a struct order in which the template type, have one template type T, an integer. Okay, you can pass known types as template argument, which is u colon colon value and type name u equal T colon colon type. You know what that is? This is a compiler error. And maybe I shouldn't show you right now since I haven't shown you other stuff earlier. But basically, this is how the things is deduced. Let's see the working example. Let's say we want to instantiate order of B. And B has a type def inside, which is B, and a static const int value, which is 100. So this is a type def in the new C++ 11 standard. It's just a type definition, and type will be equal to b. And value is a static constant value, which is 100, which means that is available at compile time. And now, when I instantiate order b of x, b will be substituted to t. So b will be t. Now, u is by default type name, type column t, type column types, but t now is b, so it goes to this type here. And x is u column value, which is 100. How confusing is that? Mildly? Okay, good. But the order is important. So this other example doesn't work because the template arguments are evaluated from left to right. So when I do x equal u column value, u has not been seen so far. U is defined in the same line, right? It should be possible to solve it somehow, but it's not. C++ doesn't go and look on this line for the symbols. It defines from left to right. So this doesn't work because u is not defined here. But this guy actually works because u depends on t and x depend on u, and they're all defined on the left. Default template arguments. We have seen an example right now of the default template arguments. From C++ 11, you can have default template arguments on function templates. Before it was only for classes. Of course, it is valid only for arguments which are on the right, right? Because you have to, the only one that can be defaulted are the one at the end of the list, not the one before, like for function default argument. And for instance, in this case, we have function foo 65, which by default return a char. So foo of 65 will instantiate t as an integer. The result type is a char, and you have to static cast the result to result of x, and this will print the capital A, which is the ASCII code of 65. But foo of int will print 65. Is it clear to everyone why this happens? So, I repeat, I see some faces that request some explanation. Foo 65. Foo is a template function. 65 is an integer. I'm requesting foo of int 65. Now, it finds foo here. The type t is int, because I know it from here. And the result type has not been specified here. So it's char. It's like for functions that have a default value, int x equal 10. If you don't specify x, that will be 10. Otherwise, you can pass a value. So exactly in the same way, this guy would return a char because the result is by default a char. Foo int, and I need to specify both of them because the first argument is this guy, and the second one is the result. If I put foo of int, that will have the same effect. These two guys, the first two invocations are exactly the same function. Int 65, this is integer, will instantiate int. This will instantiate the same function. Actually, This will instantiate exactly the same function. So the compiler will instantiate only one, okay? It will instantiate the foo int with this guy, and when I call this guy, I say, okay, I already have it. I don't instantiate another one. So these are exactly the same function call, exactly the same function call. And the second argument is not specified, is left by default to chart. In this case, the second template argument is forced to be integer, and so it will be printing 65. Better? So you can have the default template arguments for classes. That's the typical use, actually. Function templates usually don't have many default template arguments. You can fully specify the all arguments. For instance, I have my container, which takes the type name t is a double and the size of 10. By the way, again, this is an integer which is passed as a template argument. So not only types can be passed as a template argument, but also integral types. Chars, int, unsigned, pointers. So this is a constant compile time value, which is called size. But to instantiate it, you need to specify the open and close angular bracket. And why? Because without this angular bracket, my container is just a template, is not a class. You specify the open and close brackets, this becomes the my container of double and 10. My container of 100, of course, is an error because the first template argument is not an integer, it has to be a type. It doesn't find the thing, oh, it's an integer, it's the second argument. No, it's the first argument, it has to be the right one. Okay. What happens with the full template arguments and specializations? You have my container of x, my container open and close bracket is x double and 10. What happened when I do my container int of x? What line is actually instantiated with y? Let's do some code analysis. So when the template is instantiated, it will always go and search for the primary template, which must be available somewhere. That is the prototype of your function, of your class. So first, when in all these cases, it goes and searches where is the primary template. And the primary template says, okay, look, this is integer, and the second one is default, so it will be int and 10. Then it will look for the specialization that matches, in which case it will be the second one. Also in the first case, actually, even for x, it goes to the primary template, it puts double and size 10, and then it goes here and says, look, there is a specialization for the case in which the size is 10. So I will call this specialization. So this will instantiate the specialization with 10. This also specialized with 10. This even more. Yeah, we specialize 10, so it goes here, override the default value. This one goes to the primary, because 30 is not in any specialization. And this goes to the specialization with the size 15, because it goes to the primary template with the integer, and the size will be 15, and then it looks for the 15, it looks if there is a specialization that helps with that size. Does it make sense? Remember, always look for the primary template first, and then search for the specialization. As we already seen, the template arguments might be different from a type. We usually say we pass a type as a template argument, but we can also pass values. For instance, this is a good way of implementing a static integer. And static integer is just that value. So stdc out of static int of 5 will be just printing 5. So why is this useful, if it is useful? It is useful when you create abstractions that requires these values to be passed back and forth everywhere. And you just have to, this is basically a concept of a static integer which contains a value static field, and you can read it, and you can take this guy and do operations at compile time. We will see this with template metaprogramming. Okay, the real deal. How many of you have heard about the SFINAE? 1, 2, 3, okay. SFINAE stands for substitution failure is not an error. Now, you are looking for specialization. You are a compiler, and you're looking for specializations. Among your 100 templates, specializations, you're looking for the one that matches the best with your case. There might be some of them for which the template substitution doesn't really work. For instance, in this case, we have a specialization that takes a type T and requires as a second template argument, instead of int, or instead of whatever, we require T column extra type. A T column extra type is a data member, is a type member of T. Right? So T has to have a type def inside, which is called value type. It's called extra type. And well, when it goes there, you pass an integer. What happens? If T is an integer, int column extra type doesn't mean anything. It's actually an error. You cannot do int column extra type. So this should be a compiler error, but it's not. It's silently disposed of. This guy, in case of T is integer, will be simply be replaced, will be put aside and silently ignored. And why? Because it's a good idea. Because I want to instantiate x with T in integer. And if I need this extra thing, I don't see why I should complicate my life somewhere else. In case they all fail, so in case they don't find any specialization that fits, then you get the error with all the possible options the compiler tried. And say, I tried this one, but template substitution failure. Try this one, but this other thing happens. But if he finds one, he just pick it up and doesn't tell you anything about it. And I live with this before showing you, hopefully, what this is good for when you do in your code. Why to want to exploit this SFINAE in your code. And we can go with a coffee break, I guess.